So, on with the show, and going to talk about one of my favorite topics, because it's kind of important to the network that I'm involved with, MPLS-TP, the new generation of transport networks, and one of the people who's been behind the MPLS revolution about as much or more than just about anybody else, Luca Martini.
Thanks. So I will try to entertain you for the next 30 minutes. Unlike the schedule suggests, this is not about multi-protocol TLS, but about multi-protocol transport profile. So this is the agenda. We'll go through what problem we tend to solve, and an overview, and some standard update. Okay, what problem is being solved here? In today's networks, the biggest application is the packet-based IP transport. So it would be nice to move to a technology that matches the service better than the traditional SONET TDM technologies. So we want to have a lower cost technologies. We want something that goes higher bandwidth, much easier, although they're pretty much tracking each other, but the cost is not. Packet-based ports seems to come down significantly in the recent years. But what we want is we want to maintain the transport characteristics through the technology transitions. So things like predetermined path, in-band OEM, fast detection and recovery time, and NMS provisioning. This is what all the characteristics of the transport network. I've been trying to preach this for about 10 years, and all the transport people will always tell me it's IP, it's too difficult to manage and implement, and you probably disagree with that, but there was nothing I could do for a long time until this MPLS-TP came along, and it's basically MPLS for transport folks. So in the past, we'd have the whole TDM network. The application was just voice. Today, we're getting packet is growing. TDM is shrinking. If you look at any network, the internet is the biggest traffic generator of most networks, I would say, not all. There are some aberrations out there. And then in the future, we're going to go to all packet. And how we're going to do that? It looks like today MPLS-TP is the leading contender. So, as I said, the carrier Ethernet will replace SONET SDH as the encapsulation for over the fiber directly. What we want to do is find a technology that creates transport circuits in a better way than doing TDM and SONET. So a little bit about the transport world. Transport world believes in circuits only, point-to-point circuits, statically provisioned, long-term. Things don't really change that often as far as connectivity to devices and things like that in that particular level. And they want to have very simple to understand OEM mechanisms, and control plane should be a static NMS provisioning, nice graphic GUI. So the transport world has a little different view than on IP MPLS than we might have. They don't really understand IP. They think it's very difficult and to assign IP addresses and maintain all of this. Very complex IGPs. They don't quite understand that by using these IGPs, we make the network scale better and be easy to operate, but instead they think that this is an added burden and a cost that's not necessary. We have poor and inconsistent OEM. Of course, we know the OEM in IP works really well, but they don't think so. So we're trying to make MPLS transport friendly. So we start, we're doing what transport world wants. We do everything static. Everything gets managed by the NMS, like pseudowire and LSPs. We have OEM in band with LSP, and we can add multiple transport protection mechanisms with MPLS, so we don't have to just do the simple active and backup LSPs. We can actually work on more sophisticated things as well. So we want consistent OEM capabilities in band between the layer 2, the LSPs, and the pseudowires, which are today they pretty much only client defined for an MPLS-TP network. So how does MPLS-TP concept? Well, basically what it is we have a statically provisioned LSP from one P to the other through core router. We have an in-band OEM channel that is used to pass OEM between the routers, and of course the middle routers, which are called MIPs, MIP points, can also inject OEM if they detect an error or things like that. And what we run a pseudowire from the P to the P so that you can actually transport the client signal, which could be Ethernet, ATM, or whatever protocol you want. One point to show here is that this maintains the MPLS hierarchical nature of having LSP nested within LSPs or pseudowires nested within LSPs. One thing to note, though, is that while in SONET it's very well defined how many channels you can put in one particular STM1, in MPLS-TP it's not. It's like MPLS. You can put as many as you want, which presents some challenges at the OEM level for scaling the amount of pseudowires in an LSP. So everything is done by network management, as I said. So it's MPLS static labels provisioned by NMS. The control plane is very simple, and it's just an OEM. It's responsible for determining if circuits are alive, like continuity check, continuity verification if somebody actually has unplugged the fiber and plugged it into somewhere else. Because remember, there's no IP addressing on these, and so there's no, there's no IGP or anything like that that would detect that somebody swaps the port. So we have to put that in NMS. So some major observation. I'll go through the details of this afterwards. We are adding an associated channel to the LSPs. Before we just had MPLS LSPs, which were relying on IP to do the OEM. Now we have to add a different set of OEM functions which don't rely on IP at all. And so they are similar. Some of them are similar to what we could do on pseudowires for the past 10 years, which was running, for example, BFD on an associated channel. We want to avoid breaking any MPLS architecture function. So this should be very compatible with MPLS. We were not changing any function there, so we're just adding to MPLS. So in the end, as I say on the last line, there is no change to the IETF MPLS architecture. And this is one of the biggest arguments we have on the standards MPLS-TP lists. Because there's always somebody that doesn't understand how the architecture works and proposes an addition that will break the MPLS forwarding paradigm. One other major change from IP or MPLS is that the paths, the LSPs, are bidirectional only. We're not going to have a single direction path with this technology. This is to maintain the circuit characteristics. It's also to allow for timing, time of day transmission, which is a requirement coming up in the 4G networks, LTEs. If we have non-bidirectional paths, we have issues when we do rerouting and things like that. So we actually decided to go with bidirectional paths only. What is this? Oh, went the wrong way. Let me show you a little bit what the packet looks like here. I'm going to assume that on the left there is a MAC header, so this packet rides over Ethernet. It doesn't have to, but that's most likely what it's going to do. There's two labels. This is a pseudowire. Actually, this is an OEM packet. And so there's two labels in here, the LSP label and the pseudowire label, let's say. And then we have a GAL, which is a special reserve label, which we actually, Dave, I think they got the number 13 for. And this is used to basically indicate that the next, afterwards, the next piece of data afterwards is actually a generic associated channel header, because there is a implied function in MPLS where if you expire the DTL at some random node in the middle of the network, the packet gets sent to the processor for interpretation, and it's always interpreted as an IP packet. So the first thing that the processor will do is look for a 04, 06 in the first nibble of the packet and go from there. And this one is not an IP packet, so we kind of have to say, well, this is not an IP packet, go interpret it as a generic associated channel. And here we have a few things in here. The terrestrial part is the channel type, which tells you what kind of payload is after that. And so with this method, we're able to create an in-band channel along the LSP where we can actually run things like BFD or OEM messages, like telling the peer that we have a link problem upstream, or things like that. AIS-like messages and so forth. So this is an example on how the LSP OEM works. As you can see, I wanted to first define the terms, and basically we have, similar to the SONET world, we have the round circle, the orange circle here are maps, which is the maintenance endpoints, which is where LSPs would end, and the middle point are called MIPS, maintenance intermediate points. And what you can do in those particular points, you can inject OEM messages and take actions like injecting LSPs down, injecting OEM messages, and so forth. This is a simple example on how the alarm propagation is changing, is actually used. Let's say we have a failure and a link P2 in SP3 here. The first thing that will happen is the two PEs will detect the failure, either by loss of light or maybe because they continue to check the BFD session has gone down. They then send a message, interface down in packet terms, to this MIPS, the map SK here, because it's an endpoint on this part. This is a multi-segment pseudowire example, which means that TP1 goes to SP3 and then SP3 to SP4, and then there's another segment, SP4 to TP6. So there's like 3 LSPs and 3 pseudowire segments here that we're looking at. And then the next thing is the MIP0 will send an AIS alarm. It's actually been renamed this lately. To the TPE, and it also then what we do is the SP3 and TP1 send an interface down, because the TP1 received the AIS alarm, and this interface down is then sent up to the map, which is the pseudowire map. So pseudowires have maps as well. They don't really have MIPS at this point. We had a big discussion on this, on what it is really, because the pseudowire predate this technology, and therefore it's not quite a MIP or a map. But we then decided it's a pseudowire map, and then at that point, the pseudowire will send an AIS alarm, which is not really, in the pseudowire terms, is a TX failure. In this case, actually, an RX failure alarm in this direction. And at this point, the pseudowire takes appropriate action, signals the attachments. It could be Ethernet, could be ATM, that it has gone down. But before it does that, actually, it tries to find a backup pseudowire if that feature is enabled or not. And then it says, if I can't find a way to fix this, then I will send a message out to my client saying that this channel is dead, and so maybe the client can do something else. This is a quick update. Before I go into this, I want to say the IETF is now working very hard on this technology, and there's a lot of meetings and a lot of people putting an incredible amount of hours in this. This is unlike most of our technology I've seen. And so just to give it an example, usually they have one working group meeting, as you probably know, for one technology, and here we have 3 meetings, 4 breakout sessions, just official ones, but then they have over 20 other meetings between a smaller group. So progress is being made fairly quickly. There's a bunch of RSC out already. You know, this is kind of an idea of what the problems that we have today as from the last IETF. You know, there's a kind of a unidirectional link protection, for example, that's really not possible to deploy. You know, there's still a BFD discussion ongoing. I believe they actually reached a solution on this about a week ago. You know, so this is moving fairly quickly. We'll have the results in the next IETF. The static pseudowire protocol draft, which I came up with a couple months ago, is basically to put status messaging in pseudowire without LDP control plane for the MPLS-TP. That was accepted, and we're moving on with that addition to pseudowire technology. We have a map definition, and there's a ring protection, which is pretty much had a lot of presentations, but it's been converging to 2 proposals right now. One of which is very SONET-like, and the other one which is more MPLS-like, and so we'll see what happens there. You know, there's a MIP problem, which was reported by NTT. So they want to test to each interface of a box, mind you, not necessarily each IP address, like you have an IP input address and output address on the router. They want to have each interface inside the box and have a loop, a way to set a loop to it, and that's quite, that is not quite a things we can put in a protocol. So tomorrow you have a new box that has maybe 10 hops inside itself. Then you can test for all the 10 hops. So we settled on a packet format that contains a request for the hop you want to loop the packets at. So MPLS-TP, I wanted to make a point here that MPLS-TP is LSPs, and LSPs can be nested, and we can nest them from all sorts of different reasons. In this particular example, we have a provider that goes from B. Let's see if I can get the cursor. All right. The provider goes from B to E, and then provider from F to A. And so the middle provider can push another label, create an LSP, an outside LSP, which will allow him to do some OEM monitoring from E to B, and this is completely independent of what the other provider from A to F will do. He can also do OEM monitoring, but it will be end-to-end, and they both are kind of ships in the night. So we use the MPLS technologies to offer the service like if it was a native service from one provider to another. And there's a bunch of discussions here where we put the service delimitation, if it's in a pseudowire or if it's like in an LSP. And I think both models will probably work. And a little example of where this would be actually deployed. If you get a typical service provider network with an access part where you have all sort of things like EPON, DSLAM, and so forth, what the aggregation, the first part of the network would be running MPLS-TP, which is then handed off by very easily to an MPLS network if we want, or you know, the services could be injected closer to the customer at the edge here. So some services will just be injected here, and other LSPs will continue across the MPLS network. And we can do this at LSP of pseudowire level. For now, we've defined it at a pseudowire level by putting an SP here at the edge of the network. So one of the things to point out is that TMPLS, which is kind of a predecessor of this, but it was a different technology, is dead at this point. There's no more work, and it's been superseded by the MPLS-TP work. We're making rapid progress in the IETF, and everybody is behind MPLS-TP. There's a lot of interest from the whole industry to replace the SDH model. And MPLS-TP really is just OEM additions to MPLS and a subset. You know, they didn't want PHP, so we cannot do per penultimate hot popping on MPLS-TP, but that's fine. It's always been an option in MPLS anyway. And so there's no change to the base architecture. Anything we do has to be integrated with the base architecture, and there should be no changes. So all the chipset that we have today, the forward MPLS, will work fine, and we can make sure this technology remains low cost. And Cisco is leading the effort on this technology. Questions? And as you can see, we can see MPLS at the end of the tunnel.
Do you think the MPLS-TP is competing with dense wave division multiplex in a metropolitan area? As far as delivering a service for high density traffics for the customers, you think it would compete?
With TDM, yes.
Not TDM.
No.
Dense wave division multiplexing is different than
DWDM.
Right.
Right. You would run this over DWDM. I mean, that's not...
I understand, but in a metropolitan areas, for example, if you go to Washington, D.C.,
right,
is most of the governments, they do have a dense wave division multiplexing string. Right. Can you compete as far as the conversions and latencies with DWDM?
Yes, the convergence and latencies will be very good, and I would think that we could make it better than TDM networks. Some of the SONET networks are defined as a certain radius of rings and things like that, which if we do a local protection, like we can do in the future in this technology, we're not sensitive to those distances. So that's why we can actually do better than the famous 50 milliseconds. If we want to. But to answer your previous question, the DWDM, you can run anything over those waves, and so you can run Ethernet and MPLS-TP over that. And as far as provisioning, this has the advantage of statistical multiplexing of packets. You can have classes that carry Internet that are best effort. Well, in TDM you can't. You have a bunch of empty channels. So the efficiency and the fact that the cost will be comparable to TDM ADMs, for example, will really, I think, will be a great success for this technology, replacing the TDM SONET technologies.
But I believe if you're running over the dense wave division multiplexing, you're adding another layer of latencies to dense wave division multiplexings. Because you already have one, then you're going to put another one.
No, because you wouldn't put a layer on top of so you wouldn't use the TDM convergence mechanism. Right? It's not over SONET. There's no SONET, so you can't really do that. This is just packet. There's no layer of SONET underneath this.
I understand, but if your MPLS is going to run over the dense wave division multiplexing, if the fibers get cut, you're going to have a conversion at the lower layers.
No, you don't. You wouldn't have a conversion lower layer. This is the layer. There's no SONET underneath.
No dense wave division under it?
The underlying packet is an Ethernet packet. It's an Ethernet header with the labels you've seen. There's nothing underneath. There's no SONET, SDH framer or anything like that.
Okay. My second question is that on the Ethernet side, are you slicing the Ethernet framing? Because right now the carriers are providing a Ethernet framing, but what they do is they slicing the Ethernet framing. For example, if you want a VLAN as a customer side, you got to tell the carriers, hey, this is my VLAN, these are the IP addresses.
Right. So the problem is Ethernet is somewhat a competing technology in this area. It's not as scalable and as manageable than what MPLS-TP is going to be. But basically you can do both. But I would think that in the future we would run those Ethernet services over MPLS-TP, just because it is, the OEM is better. We can do it's easier to manage and so forth, and it's more like transport-like, while Ethernet is a broadcast environment. So I would think that we'll see a mixture of the two in the future, even to the point where you have maybe Ethernet on the outer rings, and then MPLS-TP as you get further into the network. But you know, it's not. Today, I would see more a little bit of its competing technology in that area.
Thank you.
And thank you very much, Luca.